We're going to talk about streaming data platforms and specifically the convergence of streaming data platforms with microservices. But before we start, we'll take a look at what's actually the problem with data platforms nowadays. And specifically, when we look at at the current audience, most of you will be working not necessarily in data, but more in the microservice and application space. And when we take a look at that, we see that this is a pretty much segregated area, usually different teams working with different tools, but with different set of problems. But if we want to take a look at what the data teams nowadays struggle with, specifically batch. Batch orientation is the big problem. They're tasked with creating data repositories for organizations and supply data to other applications, report analytics, and now ML and large language models. But what they're using right now is specifically integrating other systems, upstream systems, using traditional approaches such as generating database dumps, importing them, maybe having some polling APIs that deliver data into the platform. Why this usually fails is that most of that is heavily dependent on schedules. You need a lot of orchestrations, and updates may be missed. And what that leads to is that data sources deliver their stuff. There's an ETL process. It lands in some repository, gets processed there, and it goes to BI analytical workloads, and most of it is just late, right? And that is late. It's late because obviously there's delay due to orchestration and schedules and batches. Just to give an example, in one of our clients, logistics company, they were heavily reliant on batch schedules, and they wanted to create an application that would report to their customers when parts were delivered. It's like an industrial use case. And with their existing batch schedules, they couldn't do that earlier than 3 weeks after the parts were actually delivered. So that can be significant in terms of problems, and especially batch runs can add up in time and delays. And in addition, workflows are optimized for few but broad queries rather than a lot of lookups. So what that also leads to is that you have multiple processing pipelines that dump stuff into a data lake or data lake house or warehouse or whatever, and it basically creates what we call data swamps. Essentially, lots of different data that comes from different sources. Nobody really knows where it comes from. Partly, it's the same data set, but post-processed, and you don't know which one is correct. And there's a huge problem with determining which of these data sets is the actual truth. So this is a real issue, and it's been really hampering the ability of these teams to deliver proper data sets, proper applications within the data platforms. In addition, when we're looking at microservices that rely on those data deliveries, what they usually do is to say, okay, we have that data platform. We don't exactly know where it comes from, what they're doing. We need to do some reverse ETL, right? Essentially just taking the data that's actually been already transformed and loaded and reverse transform and load it back into a microservice landscape just to integrate it. Data synchronization is extraordinarily difficult, and there are orchestration and data ownership challenges, specifically when we're thinking about cyclical data relationships, when basically you have an emitting service that emits data to the data platform, it gets post-processed, goes back to the microservice, and the microservice does again something and sends it back, and you at some point don't really know when it started and who's responsible and what kind of change affected the data set. So all of this is a real issue. So if we just try to map it on a landscape, you have an existing, let's say, typical setup. You've got multiple data sources that emit different data sets. You've got raw data dumps that land maybe in the medallion architecture in a data platform in bronze layer. There's processing. It gets reverse ETLs to business application. There's business analytics, and you create, then you emit all of that, and you try to centralize these functions as much as possible, which creates a lot of infrastructure, a lot of orchestration overhead, and the feeling in businesses that they're spending a lot of money on platform management and on the platform artifacts without as much value, and not without leveraging the value that was promised in the first place. Now, what if we basically rethink all of this, right? Rather than having a monolithical data platform where everything is centralized and every process is essentially combined and orchestrated by a single platform. I mean, for the microservice folk, that sounds very much like the old monolith versus microservice landscape applied to data platforms. And in addition, what if you basically apply domain thinking, which is like domain-driven design, which is also common to microservices, to the data platform landscape? And also, what if we basically manage to bridge the operations analytical divide? What we mean with that is the clear segregation between data-centric processes like reporting analytics, machine learning predictions, even generative AI and all of that, and the typical service or business application, operational application landscape. How about basically rethinking all of this in a common approach to data? And lastly, what if we manage to get rid of ETL altogether, right? No reverse ETL when we talk to data platforms, and no ETL within the platforms when we basically receive the data from upstream services. That basically leads us to an approach which we called data products, basically using streaming data platform architectures to design data products, was essentially a fancy name for a microservice approach to data services. So what that actually implies is that you basically think of a data product as a service that unifies stream processing, like event sourcing, with the storage of data, the infinite storage of data, not necessarily just let's say the transactional storage, ephemeral storage, but like the forever storage, long-term storage of data sets. And when you think that further, you basically have a service that owns the relationship to upstream services and represents the data in all the ways that are necessary for business purposes, essentially when other services request data from the data product, and analytical workloads. So essentially, and in addition, data products are not organized in a central platform, but rather in what we call a data mesh, which is also another buzzword. But what it describes is essentially not a single monolithic platform, but multiple data platforms or little data platforms, aka data products, that are run separately and are segregated in their own landscapes, but integrated together. So what that essentially looks like in terms of principles, and that is also very similar to microservice design, we basically have decentralized ownership with clear domain boundaries. So essentially, every data product has a set of data entities that they own and represent. They're source agnostic, so they can source from different systems, upstream systems, and represent everything. So it doesn't really matter if you want whether the data, input data that for a specific domain is sourced from an SAP system or from IoT devices or a combination of several sources. They basically don't care. They're agnostic and they represent the data regardless of where it comes from. They're self-contained. So they basically hold the raw representation and its enriched state and the associated metadata. And lastly, they provide standardized interfaces. So they basically use standard protocols like message-driven protocols and for asynchronous and HTTP-based protocols for synchronous access. So What that also requires in terms of principles or approaches is what we call shift left. I mean, what shift left means is that we, instead of keeping the data as raw as it is for as long as possible, and essentially letting the consumers process the data, which is the standard pattern for ESBs and other bus approaches. We're basically shifting the responsibility for processing and enriching further left, so further upstream, into the data products. They contain all the logic that's necessary to cleanse, curate, and validate the data that they inherit and manage. And they have clear data contracts. So essentially also what a data product is a sort of a service level implementation of the medallion pattern, which basically has like bronze, silver, and gold, with raw data landing and storing, curating and validation, and representation for silver and gold. So all of that is part of the shift left approach of pushing the processing and curation further left in the flow, further upstream, rather than giving all the consumers the responsibility to do all of that on their end. And in terms of the access to data services, we differentiate between two different types of consumption patterns. One, obviously, is the continuous delivery of streams of events, which is essentially how data services communicate amongst each other, and consumable endpoints for consumers, which is either a subscription, where you basically subscribe updated snapshot events, or you basically query the data product for a specific incarnation and snapshot of the entity that you're looking at as a keyed record retrieval at an HTTP endpoint. Important is that all of those interfaces are guarded by data contracts. So enforceable schemas that you could say we can rely on the fact that the data is presented in a uniform way with a validated contract that you can rely on. When we're looking at how a data product generally is built as a pattern, we're basically looking at several building blocks, one of which is Apache Kafka, which is the de facto standard for message brokering. Of course, you can build a data product with other technologies. There are some advantages in using these as in terms of integration and tooling, right? Specifically in Kafka's case, there's hundreds of integration patterns and integration products that you can use with Kafka Connect. Upstream system integration is quite easy. In terms of stream processing, you have more options. You can obviously implement microservices within a data product with something like Zio, for instance. That's a very well-suited framework, especially in the Scala crowd, to do stream processing within a microservice, message-driven microservice landscape, which basically inherits and is adapted to the data product approach. Kafka Stream, Spark, Flink, Quix for the Python crowd are other stream processing framework that allow us to do transformation, cleansing, curating, and projection within a data product. If we want to take the SQL approach, we have stream query engines such as Rising Wave, Materialize, or Flink SQL that allow us to express the same kind of projections and aggregations, but just using SQL instead of writing application code to do that. And lastly, in terms of storage, we're looking at Iceberg, which is rapidly becoming the standard for open table formats. There are others, obviously, like Delta and Hudi, and Apache Xtable, which is incubating, which are all open table implementations for long-term storage of data in data platforms. So if we just basically piece that together into a data service architecture, we're looking at the unification of batch and streaming into a single platform architecture, which serves real-time subscriptions, lookups, and batch retrievals. So essentially, we have multiple upstream systems, let's say SAP, some RDBMSs, maybe Salesforce, IoT, whatever, buckets. We use Kafka Connect with its connector architecture to continuously stream the events from those upstream systems, put them in input topics. We have data normalization and aggregation, processors within the data product with a continuous snapshotting a data repository, which basically gives us the ability to either expose a stream normalized stream outflow to a streaming application, or real-time API for static lookups or batch retrieval directly from the data repository. So essentially, we basically serve multiple use cases with a single architecture, which is continuously streamed in near real time. So if we're looking at the individual components, as we discussed earlier, Kafka is like the tool of choice. It's the most popular data integration platform. And in combination with Kafka Connect, we have the ability to just plug and easily integrate multiple sources and destination systems. There are hundreds of different Kafka connectors that allow us just hooking up, doing CDC from relational systems or other storage systems, or just inheriting change sets from IoT or other ERP systems quite easily with a normalized output and schema support. Fairly easy because basically it removes all the pain out of the integration use case, which used to have to be coded explicitly. Now you can just plug and play, sort of, right? Of course, the devil's always in the details, but you can plug that and configure that problem, most of that problem away. We have snapshot ability. When we're basically streaming the stuff out of Kafka, we can basically write it straight into Iceberg tables or Delta QD, but Iceberg is quickly becoming like the de facto standard, especially now with Amazon's announcement that it will natively support Iceberg in S3 tables. It's seeing a lot of traction there. The advantage of open table format is in comparison to, let's say, more traditional approaches such as Parquet, that you basically have the ability to do merge upserts within the same data sets. So you can essentially continuously write and update your data sets to a bucket object storage and handle continuous snapshotting without necessarily having to implement manual processes to reconciliate and compact your data sets. In conjunction with a metastore, you can also query that just using simple SQL with a SQL engine. So it makes it fairly simple to do to execute queries on top of that format. Obviously, just snapshotting raw data is not going to cut it. You want to do some transformation, and you have like multiple options. In-stream processing can basically, on a very simple level, if you're just looking at just Kafka to Kafka communication, you can use KSQLDB, which is essentially a SQL engine for topic-to-topic transformation. Fairly simple, but just good enough for relatively simple aggregations and processing requirements. If you want to do a bit more, you'll have to use a stream processing framework such as Spark or Flink or Kafka Streams to do more complex aggregation and implement application logic in your stream-to-stream computation, which then can basically process raw state to projected curated state and let's say, implement the business logic that's required within your data product. Lastly, we're looking at the projection capability. We're just taking a bit of a step back in terms of what the data product needs to project to its end consumers after post-processing. We want to be able to say, we want to create a bespoke representation of a schema or an entity for a usage pattern, and can be composed from different sources. So essentially, we want to be able to continuously project joins or aggregate joins from multiple streams within a data product, which results in a materialized view. So if we're thinking about this like relational database tables, you basically have two input streams that can be represented as tables. We create a view as a projection, and that view can be materialized. And in terms of view materialization, we have several options. We can either do that programmatically in code, or we can use an in-stream query engine that does that computation. We're going to take a look at two different options. One is Flink SQL, which is essentially a SQL macro language on top of Flink. Essentially, you express SQL in Flink, and it does a computation and translates it to aggregation programs that then create a dynamic table representation of the streams and compute an output stream, which can be then a materialized view. Or Rising Wave, which is a completely fresh in-stream streaming database that speaks the PostgreSQL syntax. That does essentially the same thing, but gives you essentially a Postgres-like look and feel and implementation for stream processing. It scales very well for large scale operation, and it gives us the ability to create intermediary tables that are then stored in between without having to resort to Kafka. So you basically have an additional option in terms of projections. It's very well suited for, let's say, complex use cases with a lot of different queries that are auto-generated and need a lot of different complex joins. We've done that in a project where we're basically mapping 700 different tables to view representations, and we didn't want to do that by hand, nor did we want to code that. And Rising Wave gave us the ability to generate views that would be computed on the fly in dynamic queries that would be materialized to the consumers. So when I take a step back to the actual implementation, a data product and its anatomy owns a domain and has projection capabilities, can implement one or several connectors to different upstream systems, merges that in multiple input topics, gives us the ability to normalize those data flows, can either implement stream processing aggregation or use a query engine to do the projection using SQL with continuous snapshotting to data repositories and outgoing topics. So essentially, we provide a lower code implementation of a data product. And lastly, when we look at the architecture of a data mesh, we have multiple variations of those data products in the data mesh. So we can combine different data products with different implementations, all of them using, let's say, the same ingestion pattern using Kafka and Kafka Connect, but with different combinations of the tools that we have that we just looked at. It can be a combination of Flink and Iceberg with Kafka Connect, or Rising Wave and Kafka. We can have zero microservices for a different entity. So essentially, it gives you the same kind of flexibility that you have in microservice land, where essentially the stack is decided on a per microservice basis, rather than having to use the same stack implementation for everything like you would do in a monolith. It's tied together by Kafka in between. So in-service, in-data product communication is handled through Kafka. And we have, let's say, a uniform representation of uniform access across multiple data products, regardless of their implementation, by providing outgoing topics for subscription or query APIs for different consumers, which can be obviously across the board, either business applications, Gen AI, machine learning pipelines, basically are going into vector stores or feature stores, or even BI dashboards and analytics products. So essentially, what this approach and architectural approach gives us is the flexibility of microservices with, let's say, a bigger tool set of things to choose from to basically implement the data needs of an organization. Thank you very much for this talk.